Hi, everybody. I'm Austin Terrell. I'm the Adult Programs Coordinator here at the Denver Museum of Nature and Science. Thank you for joining us for 60 Minutes in Space tonight. It is a pleasure to see all of your lovely faces here. I'm here to do a little housekeeping, let you know what's coming up as far as programs. We have some really exciting things coming up on June 5th. We're going to have hosting a conversation with an esteemed Danae Weaver. Danae Navajo Nation Weaver, Linda Teller-Pete. We'll be joining two pieces of a Danae dress during the day, and we're going to be discussing the practice, as well as one of our conservators is going to dig deeper into that June 5th. Really excited for that program. Anybody heard of Science Lounge? Science Lounge? Yeah, Science Lounge coming back in June 20th. Prom for all, dress fancy and sip some drinks, and we're having some shows as well as mini lectures by Dr. Aaron Baxter, planetarium shows. It's going to be a blast, so come out and join us for that. And then at the end of the month, if you haven't gone to see, anybody seen orcas yet? Gone up to see orcas? Gotta catch orcas. Our shared future. It's the temp exhibit right now. We actually have the artist that carved the enormous reclaimed cedar whale coming down from Canada to discuss their artistic process, as well as some of the conservation work that they do up there in Canada. That is going to be on June 25th at the end of the month. So thank you so much for coming out tonight. And without further ado, Dr. Chun Yu.
All right. Thanks a lot, Austin. So how many of you are here for the first time for 60 minutes? Raise your hands. Okay, so maybe a quarter of the crowd. Well, welcome to 60 Minutes in Space. And my name is Chun, as Austin says, and I'm actually an astronomer here at the museum. I'm actually the only astronomer, the only person in our Space Sciences department. But we do this program monthly, and the idea is to give you, the general public, a sense of all the wonderful news about astronomy and space sciences that has come out in the past month. And because an astronomer by training, what I do is I typically like to choose stories that I'm interested in and that I feel like that I can actually dig kind of deeper and give you a little bit more understanding about the science behind these stories than what you would normally get if you saw a piece on the news, or if you just went to even, say, a NASA website and learned about the same story. So that's kind of the goal. And usually, there isn't any math or anything too complicated, but it turns out that I will have some math. But I'll warn you, and you don't absolutely have to pay attention, but hopefully it'll still be interesting. So with that, we'll have a chance for Q&A at the end, so feel free to save your questions. But if there's something that you're so burning to have answered right away, feel free to raise your hand or shout out, because I think we're going to turn the lights down just so it'll be easier to see the screen. So with that, I'm going to jump to the first slide, which is actually, this is something that I've been experimenting with over the last several months. And this is where I actually will have a chance to actually submit a question to me, and then there will be an opportunity in upcoming 60 Minutes in Space where I'll pick a question, not quite random, but I'll pick a question that's been asked by the audience that I'll attempt to answer at a future event. And so there will be a QR code at the end of tonight's presentation. So, and then I'll actually, turn out that I'll answer two questions that were submitted in the past month. So if you have something burning that you wanted to ask me from this presentation tonight, or something just about astronomy or astrophysics or space science that you don't want to ask me in person, feel free to submit it at the end of this evening when you see the QR code. All right, so with that, I'm going to jump into my first story, which is about the Euclid satellite, and this is not from NASA. If you look at the letters at the top, that's ESA, that's the European Space Agency, and so if we can bring the lights down, but this mission was launched last summer, 1st of July, and And the satellite is named Euclid, which you might remember from your high school days. This is the ancient Greek mathematician who invented geometry. And the reason they named it after Euclid is that they want the satellite is to help astronomers and cosmologists, scientists who study the universe, to understand the shape, the geometry of our universe. And it was, like I said, it was launched last year. It's about half the size of a school bus, if you think about how big of a school bus is. And it's designed to basically map galaxies. And so it was launched, as you can see in some of the subtitles, to what they call the L2 Lagrange point, which is where the James Webb Space Telescope was launched. So it's actually orbiting close to the Earth, but it's opposite the sun. So it's always going to be opposite the sun as the Earth orbits around the sun. And so here's the launch. It launched from a SpaceX Falcon 9 rocket.
2, 1, ignition, liftoff. Spacewalk propulsion is nominal. Vehicle is pitching downrange.
So the Euclid satellite is in the payload space, which is at the very tip of the rocket.
To prepare for max Q, which is coming up at T plus 1 minute,
Power and telemetry nominal.
1 minute and about 12 seconds.
Stage separation confirmed.
And of course, what happens with Falcon 9 rockets is that the stages actually return to Earth. And so we'll see that in just a second.
Some really cool views of MECO stage separation, and on your right-hand screen, you can see that the MVAC engine has
Both
ignited.
vehicles are following nominal trajectories.
There you can see that the MVAC engine has shut down, and the landing burn has begun on the first stage vehicle.
Expect a loss of signal, Kate. Nominal orbit insertion.
So it's always fun to see those return back to Earth. And the Euclid mission has two instruments on board. One of them is a spectrograph or spectrometer that can basically measure fingerprints of elements, and that will tell us a lot of information about the distances to these galaxies. But this is a kind of a composite image of the other instrument, which is an imaging instrument. And actually, both of these instruments cover roughly the same size or footprint on the sky. So you can actually see how massive this detector is. So there are 36 separate detectors, and each of these detectors is 4,000 by 4,000 pixels. So that's 16 million pixels. And you can basically snap an image on the sky that's larger than the full moon. And the idea is to map roughly about a third of the sky. So what we've done here is we've taken the entire sky and flattened it onto this ellipse. And so here we have the Milky Way that's running across. And then if you look really faint, you look closely, you can actually see kind of a very faint glow that it looks sort of like an S shape. That's actually what's known as Zodiacal dust. That's actually very faint dust glow from our solar system. And so you can see the regions that Euclid has started mapping avoids regions in our Milky Way and in our solar system that can confuse or block the light from galaxies that are further in the background. So here is just an animation showing the coverage that Euclid makes. And so this is about a 6-year mission. And what this means is that by the end, they'll basically have this completely mapped towards the end of the decade. And there are you can see 3 yellow splotches, and those are regions that are known as the Euclid deep fields. And so you might have heard about the Hubble deep fields. These are regions where the satellite will just stare at that part of the sky to get these extremely deep images to get really faint galaxies. And so what will it do? Basically, when it images the part of the sky, you're seeing a kind of a 2D footprint, like we saw earlier in that image with the moon. But in effect, what you're doing is you're sampling a huge wedge of space that goes from nearby galaxies that are close to us, and the light that is emitted from them are very close to our present day. But because as you look further and further deeper into the universe, that light takes a long time, can take potentially billions of years to reach us. And so at the other end, you're seeing galaxies that are very distant. These are also galaxies that have emitted their light in the past, and it's taken that length of time to reach us. So basically, Euclid will, when you get a 2-dimensional image that compresses all this information, but using the spectrograph, the spectrometer on board, astronomers will be able to basically figure out the 3-dimensional distribution of all these galaxies. And not only are they distributed in space, but they're also distributed in time too. So we're looking, as we look further back, we're also looking further back into the universe. And this will help cosmologists and astronomers basically disentangle the effects of dark energy and dark matter and how the universe has evolved because of these very mysterious forces and matter that we still don't quite understand. And so the Euclid mission has just started, and you might remember last year they actually released a bunch of images, these early release images, showing just how amazing the imager on Euclid is. And so this came out in November of last year. Here is the Perseus cluster. This is a cluster of galaxies about 240 million light years away. So the light from these galaxies basically left when, I guess during the Permian period. So this is actually before the dinosaurs. If there's a paleontologist in the house, they'll be able to correct me if I'm wrong. But every single one of these blobs is an individual galaxy. So you can see that there's about 1,000 foreground galaxies, and these galaxies are all loosely gravitationally bound together. And all these little blotches in the background are another 100,000 galaxies that are further away than this Perseus cluster. And so Euclid will basically be mapping galaxies like this. Here is a more nearby galaxy. This one is only 11 million light years away, but you can see how much detail you're seeing. The Spiral Galaxy, something similar to our own Milky Way, and you can see the spiral arms. You see a lot of structure, not just the gas and dust that make up the spiral arms, but all the stars as well. Here is an irregular galaxy, meaning it has a kind of a lumpy shape that doesn't quite fit a spiral galaxy or an elliptical galaxy. This is actually only about 1.5 million light years away. So this is in the same group of galaxies that our Milky Way is in. So it's loosely gravitationally bound with all the galaxies in our LOGO group. Here is, now we're getting to, these are, this is a globular cluster that's a concentrated, basically, ball of stars that's orbiting our own Milky Way galaxy. So this is part of our Milky Way. It's about 7,000 or 8,000 light years away. And again, all these stars, on the order of about 100,000 of them, are gravitationally bound together into this big blob. So these are the images that were released last year, and now we're getting to the latest releases. So this is about 2390, and this is the furthest cluster of galaxies that they've released an image for. So this is about 2.7 billion light years away. And There are stars. So you notice that there are point sources that have those spikes next to them, and those spikes are not in the original objects, but they're an artifact of the light going through the optics of the telescope, and they show up from bright point sources. And so galaxies are extended, meaning they're not point sources, and so they don't tend to show points like that. So you can tell where the foreground stars that are actually in our galaxy are located just by looking for those diffraction spikes. But here, again, you can see there's kind of an overdensity of galaxies towards the center here, so that's where the Abell cluster is. But again, there's lots of more further background galaxies as well. But there's basically 50,000 galaxies in this one image. All right, here is another Abell cluster, but this one is off towards the upper right corner. So it's off towards the top, and this is about 1 billion light years away. And again, here is a super bright star, because you can tell that there are these diffraction spikes coming from them, and that's again due to the light bouncing around in the optics of the telescope, and that again is a star in our own galaxy in the foreground. Here is another wonderful spiral galaxy. This, again, is relatively nearby, about 30 million light years, which is why you can see so much detail. Here is a galaxy group in the Dorado, it's known as the Dorado group, and we're actually seeing two galaxies that not only are close together in the sky, but they are close together physically as well. And so it turns out that when you have lots of galaxies gravitationally interacting with each other, it's actually quite easy for them to get close to each other, to merge and to collide. And so we're seeing part of that going on. All right, so now that we've, I seem to have lost the, okay, it looks like we're going to get help.
Restart the extender for you real quick.
Okay. So we've had issues with the video cables. Should I escape out of here? Okay.
I'm gonna run back there and switch it real quick.
Okay. All right, well, while we're waiting for the technical difficulties to be resolved, I can answer any questions that people might have. Yes?
How can you tell the difference between a star in our galaxy and a star that's in a galaxy?
Yeah, so that's a really good question. You know, I was talking about stars in the foreground of these pictures, and I said that they were all in our galaxy. And so the question is, how can you tell the difference between a star in our galaxy versus a star in another galaxy? Well, the galaxies that we're looking at are so far away. You know, even when or even the closest one was about 1.5 million light years away. So at those distances, the stars would not appear as individual points. So the reason why galaxies appear as fuzzy glows or nebulous shapes is because you're seeing hundreds of billions of stars emitting light from light being emitted from those galaxies, but the starlight is basically smeared together along with all of the, the light from an individual star is smeared along with the light from all the other stars. And so as a result, the more distant stars you can't actually see. They're lost in the glow of all the other stars. So you can, if you see an individual star like here, that is coming from a much more nearby star. So here, you're seeing the glow from hundreds of billions of stars from this one galaxy. You can't see the individual stars because the individual light from each individual star is so dim, you can't make the individual star out. It's only when you look at the stars collectively that you see all of them via that glow. Okay, so that's all I have for Euclid, and that's just because they haven't announced any real science results yet, only the pretty pictures. But what I'm going to do next is talk about some real interesting science results, mostly from the James Webb Space Telescope. So we're going to go from the European mission to the American mission, and the first paper has to do with observing the oldest black holes from the James Webb Space Telescope, and this is from a paper by Minghao Yu from MIT. And basically, the idea is, people always wonder, how can we observe black holes, or how do we know black holes are out there? And most of the time, black holes are observed indirectly. And this is an example of observing black holes indirectly. And the easiest way to look for black holes is to actually look for them at the centers of other galaxies, of distant galaxies. And it turns out that many galaxies today, and most galaxies in the past, early on in the universe, were powered by black holes, meaning they had a central supermassive black hole engine at the centers of these galaxies, and as gas spiraled into these black holes, they get jammed up into this accretion disk, this disk of material that's in orbit around the black hole, and the friction of that gas interacting with itself can raise the temperature of this gas to millions of degrees, and so that can drive lots of energetic radiation that we can observe. It can also drive these bipolar jets of material that shoot out from these galaxies. And so we can actually observe the very energetic radiation and jets being emitted from these galaxies because of the central black hole engines. And we first knew about these active galaxies more than 60 years ago, basically from the 1950s. And some of you might have heard about the so-called quasars, which were these quasi-stellar objects. That's why they were called quasars, because they combine quasi and stellar. And these are extremely bright objects that appear to be very far away. And they're very mysterious for many decades. But with much more modern instrumentation, like the Hubble Space Telescope, astronomers realized that these quasars actually were associated with galaxies. And so this is a very early quasar that was discovered, the 3C273. And with Hubble, you can actually see gas around the very bright point source. So remember, what I said earlier, that only stars show up as point sources with these diffraction spikes. Well, here you have this quasar that's so bright at its center, it basically, even though it's billions of light years away, it appears like a bright star. And the only reason it can do that is because it's so bright, it's so luminous, because of material falling towards that black hole. And so we can look for evidence of galaxies with these extremely active regions, with these bright point sources in the center. And this is what this team did. They used James Webb to look for black holes from these active galaxies. So here is an example of one of these very distant galaxies that they looked at. And when you look at it with James Webb, you see there's a point source, and this is what this particular point source looks like when you've magnified it. And I mentioned earlier that these diffraction patterns are unique to the optics of each telescope, and so when you zoom in, you can see there's sort of a hexagonal pattern to those blobs. But again, those all those blobs are a result of the light bouncing around the optics of JWST. And what they did was they actually modeled how that light gets reflected around and the shape that the diffraction pattern gives you, and then they subtract it from the image. And so once you subtract it, the point source, you basically get the light that's left over that comes from the galaxy that this black hole engine lives inside. So by doing this very careful analysis and modeling of how light interacts with the optics of the telescope, they can model that light, they can remove it, and then you get the host galaxy. And here we see examples of it for 3 different galaxies. So here's a galaxy that's where the light took almost 13 billion years to reach us. And so the image on the left is the original image from JWST. And then they show a model of what the galaxy looks like after you've subtracted the light. And then they also show you what the actual subtraction, what it looks like after you removed the point source. And so that's the image on the far right. And here are just 2 other galaxies, all about just under 13 billion light years away. So they did this for 6 galaxies total, and these are the only 3 where there was enough signal to noise to actually recover the actual galaxy itself, so that middle column. Some of the other galaxies, there just wasn't enough information for them to reliably get back information about the galaxy. And what's really amazing is that they were able to get information about the black holes. And so what they did was these red dots correspond to actual observations from JWST, and the black squiggly lines are basically models of what the emission coming from the black holes and the galaxies must be like. And so you can, with 3 data points per galaxy, you wonder, well, how much can I really trust these results? But this is currently the best that you can do. And what they basically conclude for these 3 different galaxies is that the black hole mass ranges from 7.8 billion solar masses all the way down to 1.2 billion solar masses. So these central black hole engines are already super massive, these galaxies, we're looking at them less than 1 billion years after the beginning of the universe and the Big Bang, and already their black holes have grown to massive sizes. And they were also able to estimate how massive the galaxies, the host galaxies were, and you can see that these black holes are a significant fraction of the size of the host galaxy. So these, so this is something, these are amazing observational results, but this will be something that the theoretical astronomers will have a nice time trying to make sense of. Because one of the problems right now is that when you run simulations of the early universe and seeing how galaxies evolve over time, it's actually really difficult to get black holes to grow so quickly. So the fact that we're finding more and more of these supermassive black holes early on will hopefully spur those theoreticians to step up their game and try and figure out how galaxies can evolve so quickly like this. All right, so that takes us to the first question. Now that we've introduced the topic of black holes, this is a question that was submitted to me, and it's what would happen if 2 black holes combined from Lucas. And this is something that people who study black holes have done a lot of work on already. And so this is an actual simulation of 2 black holes that are roughly the same size, and there's no gas being funneled in to confuse matters, but you can see what happens as they spiral in and then combine. The distortion around them is caused by the intense gravity of the 2 objects, and they cause the background light to curve and get distorted as they travel to us. And so, in the end, not much really happens. But there is a lot going on, and part of what's going on is that the reason why these black holes spiral in as opposed to continue to orbit is that they actually emit gravitational waves. And it turns out that objects as massive as black holes, they can distort the fabric of space-time itself. And this distortion can cause ripples in the space-time to propagate outwards. And as a result of these ripples, this black hole system, this binary system, actually loses energy. And as it loses energy, the two get closer and closer. And so here is another simulation done associated with LIGO. And LIGO is a gravitational wave observatory. And in 2015, they actually observed evidence for the merger of two black holes. So this simulation shows you the effect of what's happening. And all these red waves coming out is actually the gravitational waves, the actual distortions in space-time. So it's actually space-time getting stretched and pulled. And it's nothing that you can see, but it's something that can distort the fabric of space-time itself. So again, once the two merge, those gravitational waves stop. So the reason why that was a perfect question was that it's a lead up to this another paper that came out this month, which actually was about the discovery of a black hole merger in a distant active galaxy. So AGN stands for active galactic nuclei. And these are those galaxies that I talked about before that have supermassive black holes in their centers, and which, when stuff is falling into those black holes, they become active. They give off a lot of light and energy, shoot off jets. So this is, you can see, this is a big team of people, and the paper was written by Hannah Ubler from the University of Cambridge at the Kavli Institute there. And basically what they did was they observed this very distant galaxy. Again, this is almost 13 billion light years away, and this is only about 740 million years after the Big Bang. So again, this is very early after the start of the universe. And when they used JWST's near-infrared camera to observe the center of this galaxy, and they broke out the light so that you can basically understand what elements, what ions are emitting the light. They actually saw two different sources, meaning 2 point sources, one under the cross and then one under that kind of that sun symbol. And they associated each of these to 2 different black holes. So it turns out that when you have black holes in the centers of galaxies, the type of emission that you get can be associated with different types of black holes, with different types of gas clouds that are in orbit around them. And so the fact that they found 2 very different sets of emission lines tells them that they were actually seeing 2 different black holes, as opposed to one black hole at the center of this galaxy. So what must have happened is that this galaxy that we're seeing is actually the result we're seeing it post-merger, where it's collided and merged with a second galaxy. And after these 2 galaxies merge, the 2 black holes find a way to each other. And so it turns out that at the distance that this galaxy is, those 2 black holes are only separated by about 2,000 light years. So, that's pretty far away compared to how big our solar system is, but that's not a very big distance at all. And again, by modeling the light emission, they're able to determine that the main black hole in the center is about 50 million solar masses in size, and the other one is just over 500,000 solar masses, 630,000 solar masses. And like I said, they're separated only about 2,000 light years. But what that means is that these black holes, we're seeing the light as, and it's taken almost 13 billion years to reach us. But what this means is that today, these black holes will have definitely have merged. So this is an example of where we've actually observed a pair of black holes before they've merged, these supermassive black holes in the center of a single galaxy. All right, since we've been talking about really ancient objects, now we're going to switch from black holes to stars. And this paper is about the first stars that were ever started glowing in the universe. And this was work, again, by a big team. This astronomer, Roberto Maiolino, is also from the University of Cambridge. And if you look, Hannah Ubler, who was in that other paper, she's the second author. So there's this big group of cosmologists at Cambridge that are doing this work. And if you look at the title, it says Z equals 10.6, and that Z is a measurement called redshift, and it's basically a direct measurement of how far something is from us. And again, it turns out that we're looking at something that's very, very distant, and as a result, we're looking at things that are also very far in the past. And so the light that they're observing from this research was emitted only 400 million years after the Big Bang. And the light is coming from, is the indirect result of what we think are the first stars in the universe. And here is a graphic of stars that we know of today. So Sirius B is a white dwarf. It's in orbit around the star Sirius, the brightest star in our sky. That's about the size of our Earth. Proxima Centauri is the closest star to us, 4.25 light years, and that's a red dwarf star, so that's pretty small. But you can see, it's not that much smaller than the sun, but it's definitely a fraction of our sun. And then finally, Aldebaran is a red giant. It's something that our sun will blow up to. Actually, it'll probably be even bigger than that at the end of its life. But these are typical stars of today in our universe. And on the bottom here is a graphical depiction of what the first generation of stars might be like. So these are stars that emerged after the Big Bang, and in many ways that they're very different from today's stars. So what happens when stars form, evolve, grow, and die is that the thermonuclear fusion that takes place at their centers that allows them to generate energy, those fusion reactions also generate heavy elements. So after the Big Bang, we think that the universe began basically with just hydrogen and helium, the most basic elements in the universe, and there is like a tiny, tiny smattering of a handful of other heavy elements heavier than hydrogen and helium, but for the most part, 99% of the universe was hydrogen and helium, more than 99%. And so those first stars were made purely of hydrogen and helium. But as those stars blew up in supernova and died, they generated all the elements heavier than hydrogen and helium, and they dispersed them into space. And as that gas gathered itself again into molecular clouds and formed future generations of stars, those future generations of stars had more heavy elements, more than zero. And so basically, the later the generation of star that you're looking at, the more polluted by heavy elements there are. So our sun is 4.5 billion years old, so it's less than half the age of the universe. So it's likely to have picked up elements from multiple generations of stars in the past. And so, but because all the stars today have some heavy elements, it turns out that we don't really have any analogs of stars today that are anywhere like the stars in that first generation. And so it turns out that because those first generation of stars were almost purely hydrogen and helium, they ended up being these enormous objects, anywhere from hundreds at a minimum up to 1,000, and some people speculate up to 50,000 times the size of our sun today. Whereas today, the maximum size star that we can think exists is probably no more than 100 or 200 times the mass of our sun. So the first generation stars in our universe were really unusual beasts because they could be so big, they could generate so much energy, and they probably lived fast and died young, like the very massive stars that we still have, but they might have done them at an order of magnitude greater scale than anything that we have today. And so one of the things about these very early stars, and because of just a quirk, they're called population 3 stars, but the immense amount of radiation from these stars, they would produce huge amounts of ultraviolet radiation, and that the powerful ultraviolet radiation would have ionized or knocked out the electrons in any surrounding helium atoms. And so helium, when you might remember from your science class that helium is has 2 protons at the center. It also has 2 neutrons. And there are 2 electrons that orbit around that helium nucleus of those 2 protons and 2 neutrons. And so ordinary helium with the 2 electrons in orbit is known as helium-1. And if you knock out one of those electrons, it turns it into helium-2. So that's what that is supposed to represent, the He with the Roman numerals 2. So that's helium-2. And so we think that one way to look for these population 3 first-generation stars is to look for the helium-2 emission. So if you can find helium-2 emission, that's a really good sign, or that's one possible good sign that you found indirect evidence for these first-gen stars. I mean, you're not seeing the light from the stars themselves, but you're seeing light from gas that's been ionized, meaning an electron has been lost due to the UV radiation. Okay, so that He2, the helium-2, is important that I want to point out, because unfortunately in this paper, what the authors have done repeatedly is that they've left out the space between the He and the Roman numerals. And so as a result, you'll see a lot of reference to hell in the images, in the figures. So we're not talking about hell, we're talking about helium-2 in each of these cases. So here is a figure from the paper where they're showing, so this again was from JWST, the James Webb Space Telescope, and they're showing this very distant galaxy GNZ11. And there's actually a foreground galaxy off to the side that's a lot closer, so it appears brighter, it appears bigger, but it's basically one of the most luminous galaxies that have been luminous distant galaxies that's been observed by the Hubble Space Telescope. And its distance, or the amount of, the distance that the light traveled to us was about 13.4 billion years. And so we're again seeing light emitted only 400 million years after the Big Bang. And unfortunately, there was an error in the pointing of the telescope. And this was not an error that the astronomers who made the observations made. What happened was that in order to point JWST or any space telescope extremely accurately, they use guide stars, meaning they have these stars that they know the positions of extremely accurately, and they reference any sort of pointing that you make to the locations of these guide stars. So they chose guide stars. They chose a guide star that was relatively close by, and JWST was told to focus on that guide star and then use that to basically reference where this object was. But it turned out that there was a problem with this guide star. Instead of it being a single star, it turned out to be a binary. And so the astronomers that made this proposal to the JWST, and they got the funding, they got approval to make these observations. They prepared their observations based on the location of this guide star, and it was only after they got their observations back that the JWST sent them an email and said, my bad, or our bad, we found out that the guide star you used wasn't at the location that you thought it was. And so basically this object was offset by 1.5 arc seconds, which isn't very much, but in the world of JWST, where you have these extremely accurate pointings, it was a huge deal. And what happened was that this yellow line here, this yellow dashed line, this vertical line, basically marks the spot where they had fewer observations than observations to the left of the line. And so, what they really wanted was for that galaxy to be far to the left so that they could look at the region all around the galaxy, but they only had this region to the left of the line that they could that they could actually analyze. And so that was, they had to make do with their observations, make lemonade from their lemons. And so as a result, what they did was they looked for helium-2 emission in the red and yellow boxes. So, what it looks like, these look like Hell clump extraction and Hell extended extraction. Those are the helium-2 extraction points. And so what they found is here is a helium-2 map, and they actually saw emission. So this white box, this big white box, corresponds to this red box here. And you can see this lower image, we're showing the GN-Z11 galaxy and the brighter foreground galaxy. So you can see that the helium-2 emission, represented by these two contour lines, are somewhat far away from the galaxy. So they're probably associated with the galaxy, and it turns out if you look at the spectroscopy, it all lines up, but they're not right dead on the galaxy itself. And you can see how noisy the signal is, but here is their helium-2 detections, and I'm not even sure I totally believe this in the sense that they think that they've detected two different clumps. So that's what those Z equals 10.6 and 10.603 are. And I think you can probably make an argument, and they do in the paper, that they're seeing two clumps of gas. That's where the helium has been ionized. But it's pretty noisy, and there's not that much resolution in this spectral plot. But one of their arguments is that you only see helium-2 emission, and you don't see any other elements. So it turns out that when you see helium-2 emission in more nearby galaxies, because those galaxies are more nearby, they've had more evolution, there's been more pollution with heavier elements, you see lots of other elements, and not just helium. But here they don't see any other heavy elements except for helium. And so it seems like this is pristine first generation gas and hasn't been polluted by heavier elements. And then they also make the argument that if you think about that galaxy, that GN-Z11 galaxy, it's actually too far away for the radiation from that galaxy, from that central black hole engine of that galaxy, to ionize the helium gas. So here, this blue band represents where you would expect emission to occur if the ionization was coming from that galaxy, but that helium-2 clump, or the Hell clump, is well above that band. So whatever is causing the ionization of the gas must be something that's much closer to that clump. It's not coming from the galaxy itself, and so that's why they are inferring that this must be due to this first generation of stars, these population 3 stars. Now, this isn't the only paper in the last several months that's come out to where they've announced evidence for this first generation of stars, but you can get a sense of how much effort and how much in the noise this work is kind of the astronomers are working in, and I think with these early years of JWST, a lot of the results like this will be kind of right at the edge of detectability and right at the edge of whether you can say these results are real or not. But as astronomers get better at denoising and figuring out better ways of using the telescope, at some point we're going to get some really solid results where people will point to the results and say, yeah, this is definitive, this is real. Whereas here, we're kind of right at the edge of detection. All right, so let's move on from talking about JWST results to some new Hubble Space Telescope results. And this is an image that was released this past month from the Hubble people of the center of this galaxy, NGC 4753. And you can see it has this weird looking, wonderful kind of spirograph-like pattern of dust clouds. And we're going to look at and try and understand what exactly is going on with this galaxy. But this is a galaxy that's been observed for many, many decades. This is an image that was taken from Mount Palomar in California, probably in the 1940s or 50s. I'm quite sure when. But this galaxy is about 60 million light years away. So the light that we're seeing from it was emitted after the dinosaurs died off. And it's known as a lenticular galaxy. So, we talked about spiral galaxies earlier, galaxies with those nice spiral arms. There's also galaxies that are known as elliptical galaxies that just look like elliptical blobs. Well, lenticular galaxies are kind of halfway in between spirals and elliptical galaxies. Elliptical galaxies don't really have any gas clouds, but lenticulars do have some gas clouds, although they're not arranged in the nice spiral pattern that you see in spiral galaxies, but they do show evidence for a disk. So that's the other important thing about spiral galaxies, is that the spiral arms are in a disk. So you can make a model of a spiral galaxy with, let's say, a pizza, for instance, and you can arrange the toppings into spiral arms if you wanted to. But so here is what the spiral galaxy looks like with a ground-based photograph, a photographic plate from the middle part of this 20th century. And here is an image that was released from January of this year. And this is from the Gemini South telescope down in Chile. So this is run by the United States. And this is a modern observatory with an 8-meter telescope. And here you can see again the lenticular galaxy, which is kind of amorphous. It's sort of elliptical in shape, but you get a sense that there is a disk structure in there. But again, that disk structure is really messy and complicated. And so what exactly is going on here? Well, it turns out that people have studied this, and the definitive paper on what is going on in this galaxy came out more than 30 years ago. So in 1992, Thomas Steinman Cameron, in the lower left corner, wrote this paper about this weird dust pattern, or the molecular cloud pattern in NGC 4753. And here is what the image that they had to work with looked like. So this is an early image taken with the Canada, France, Hawaii telescope, which is on Mauna Kea in Hawaii. And earlier we were looking at detectors that had millions and millions of pixels. Well, this detector had 316 pixels by 498 pixels. So this is far less capable than anything that you might have at home, in your phone or in a digital camera. But this is what their image looked like. But you can still get a sense of that weird dust pattern even in this particular image. Now this is a negative, so instead of black on white, it's white on black. And here is the model that they made to try and explain what is going on. So basically in this model, they assumed that there was some kind of perturbation to this galaxy, say a smaller galaxy that merged and collided and merged with the larger galaxy, and it disrupted the flat disk of gas in the galaxy. And they were able to show that with this disruption, and given the gravitational fields in that galaxy, you could actually get the patterns that we observe. And so here in their paper, they show 9 different views of their model, and they show that it was actually really fortuitous that we're looking at this galaxy almost completely edge-on. Because if we were looking at it kind of straight down the barrel, 90 degrees from the other direction, you might mistake it for just a normal spiral galaxy. But because we're seeing it edge on, we can tell that it's not a spiral galaxy. It's just you've gotten this spiral pattern that was induced by this collision event. So that's pretty cool. So now we come to the current Hubble results, and the guy that we saw earlier, Steinman Cameron, he's actually quoted in the press release for the Hubble image. So that even though there's no scientific paper that came out with this image, that leads me to believe that he was part of the team that is working on this. And so, whereas we had this super fuzzy, barely legible result from that 1992 paper, if you zoom in on the Hubble results, they're absolutely stunning just because you see so much more structure. You get these crisscrossing waves of gas and dust, and I'm sure they're currently writing a new paper about what this tells us about what that early merger scenario was like. Okay, now I'm going to try and speed through the last couple of stories because we're coming up on the hour. And now we're going to get to the one part of the presentation that I warned you about earlier, where we're going to have a little bit of math. And this comes via a question from the audience from last month. What is the virial theorem and how was it used to hypothesize dark matter? From Olivia. And this might be complete gibberish to you, but it actually turns out that it's related to some of the topics that we've been talking about. And the virial theorem is basically something that arises out of physics. And and here is a simulation of a globular cluster. And so, we saw a picture of a globular cluster earlier. Globular clusters are these small, dense clusters of stars, up to hundreds of thousands of stars, from tens of thousands to hundreds of thousands. And unlike, let's say, our solar system, if you think about our solar system, all the planets, all the asteroids, comets, they all tend to orbit around the sun. I mean, you might have moons that orbit around the planets, but there's one object that has most of the mass and where most of everything is orbiting. But when you're dealing with a globular cluster, there's no central mass. There's no one object that has all of the gravity or most of the gravity. And so when stars in a globular cluster orbit, they're basically orbiting due to the gravity of all the other stars in that globular cluster. And so you can map out orbits, but those orbits are not nice and simple and easy to describe like the ones in our solar system, where the planetary orbits are all basically elliptical, and they, whereas here these orbits evolve and change over time because, as you can imagine, when you are moving due to the gravity of everything else, that can result in really complicated motions. And so the virial theorem is basically a way to describe the situation when you have, objects in orbit around each other, whether they're stars in a globular cluster, whether they're stars in a galaxy. So in our galaxy, all the stars are again in orbit due to the gravity of all the other stars, and again that can complicate your description of how these orbits work. And even when you're looking at clusters of galaxies are orbiting not around a central supermassive galaxy. They're orbiting, again, due to the gravity of all the other galaxies in that cluster. So, so the physics or the description of how gravity is causing these orbital motions is a little bit more complicated than if you have a central sun that all your planets orbit around. So the virial theorem is basically a way to describe these complicated systems, and it simply is expressed by this equation. If you have a gravitationally bound system, if you look at the kinetic energy of the objects that are in orbit, they are equivalent to half the potential energy. And we don't have time to talk about the difference in what kinetic and potential energy is. Unfortunately, I forgot to bring a ball to give as an example, but here is just a simulation of a cluster of galaxies. And so the kinetic energy is just the velocity of these galaxies. The potential energy has to do with the gravitational field of these galaxies. but you can use the virial theorem to describe the motions of these galaxies. And the way that they do that is through these equations, which you don't have to understand, but one side is the kinetic energy, the other side is the potential energy, and you can rearrange the equation so that you have the mass, total mass of that entire cluster. R is the size of that cluster, or the radius of that cluster. The V inside the brackets squared is the average velocity of all these galaxies in the cluster, and then G is a gravitational constant. And so what this means is that if you can measure the size of a cluster of galaxies, and you can measure the velocities of all the galaxies and then average them together, if you stick them into this formula, this will actually tell you what the mass of that cluster is. And so when astronomers started to do that back in the 1920s and 30s, they started to have instruments that were sensitive enough to measure velocities of galaxies, distant galaxies. They found that the masses that came out of this equation was much larger than the masses that you would assume if you just counted up the stars. And so that was the first indication that we had that there was this hidden matter that we couldn't see, this dark matter that was there that was causing these galaxies to orbit faster. So it all came out of this virial theorem. And so you can see how this relates to the clusters of galaxies that we're looking at before, because that's how astronomers, when they're looking at the Euclid results, they're using equations like the virial theorem to help them figure out the amount of mass that's in these galaxy clusters. All right, I think this is our final story, and this, again, is from James Webb, and it has to do with the Horsehead Nebula. And this is work from Alain Abergel from the University of Paris in Saclay. And we've talked about the Euclid telescope, the Hubble telescope, and JWST, and here is our images of the Horsehead Nebula from all three telescopes. We saw the Horsehead earlier, but you can see that as we get actually, I'm sure Euclid will have just as spectacular results. We just haven't seen the super high resolution results from Euclid, but we'll zero in on what is actually going on with the Horsehead Nebula, because this is an object that you've probably heard of in the past, but you don't probably haven't heard of why the Horsehead Nebula looks like a horse. It might be one question that you might have. But let's start off with the Orion Nebula, or the Orion constellation. And this is an extremely deep image of the Orion constellation. And so even though you might be familiar with it in the sky, this is an unfamiliar view. But these are the three belt stars of Orion. And the red or yellowish blob up at the top is Betelgeuse. And so that forms the left shoulder of Orion. This is the right shoulder. Can't remember what that star is. That might be Safe. This is Rigel, which is the right leg or right knee, and then here's the left knee. And hanging down from the three belt stars is the Sword of Orion. That's where the Orion Nebula is. And if you look very closely, you see a little black blob right there. That's under the star Alnitak, and that is where the Horsehead Nebula is. And so here we've zoomed in to the three belt stars. So here's Alnitak, here are the other two belt stars, here's the Horsehead, and then this star here is Sigma Orionis. And so what is going on is that the Horsehead Nebula is actually part of this molecular cloud. This is known as the Orion B molecular cloud. So this is a giant cloud of gas and dust that stars are born out of. And in this case, there's actually not that much star formation coming from this gas cloud. You can see that the gas cloud is kind of lit up. There's a glow from it. And that's due to the fact that this star, Sigma Orionis, is lighting it up with lots of ultraviolet radiation. And the radiation and the winds from that star are ionizing the gas in this cloud. And basically what's going on is, actually let's go back. The Horsehead is just happens to be a denser part of that cloud, so it resists the ionization and the winds from the star a little bit longer than the rest of the cloud. And so the rest of the cloud is eroded away from the radiation from that star. And so it's really this kind of this outcrop that's left over just because there's denser material. But over time, it's expected that even the horsehead itself will erode. So within a few million years, we won't see that structure anymore. And this region, this whole region here, where the cloud is being heated up and ionized, is an example of something astronomers call a photodissociation region, or a photon-dominated region. And the idea is that you have UV radiation or other energy coming from a star, and the surface of the cloud is here, and you get deeper and deeper into the cloud if you go off to the right. And what happens is, deep in the cloud, you have basically cryogenic temperatures, 10 degrees above Kelvin, where it's really cold, it's really dense. All of your matter is in the form of molecules and dust. But as you get closer and closer to the edge of the cloud, you have more radiation, you have more heating, and so the gas goes from tens of degrees to hundreds of degrees to thousands of degrees. And so there's a lot of really interesting chemistry and things going on where the radiation interacts with the matter. And so that's why astronomers are interested in studying these photodissociation regions, or PDRs, because of the interaction between gas and dust and radiation and other physical reactions like shocks and winds. And so the point of this research was to really start looking at the horsehead, not just as a pretty looking horsehead in space, but to understand it from looking at it as this photodissociated region. And so this is the Euclid image of the horsehead, and here we're seeing those JWST footprints. And I won't really go into details because it's the paper that was released is a lot of complicated astrophysics about these regions that are not that audience friendly. So I thought we just look at pretty pictures of what JWST was returning to us. And so what's great about JWST is that it's looking in the infrared so that you can actually peer through a lot of the obscuring gas and dust. So whereas if you look at this region in optical light, you see a lot of glow from the hot gas around the cloud, but in the infrared, you can actually look through that gas and actually see background galaxies. So that's what we're seeing, all these, you're actually seeing spiral galaxies. And again, we're also seeing lots of foreground stars. Again, we can tell those are stars because they have those bright diffraction spikes. And then here is another edge of that cloud, and we can zoom in just a little bit as well. And so the astronomers in this paper and in future work, they're studying wavelength by wavelength the structure of this cloud and trying to understand how different gases are being ionized, being heated, and from the different wavelength images that they're getting from JWST. So with that, we're running late, so I want to thank everyone for coming tonight. If you have to run off, feel free to leave, but I'll be happy to answer questions. And for those of you who are interested, here is the QR code for submitting a question to me. And our next 60 Minutes in Space is June 26th, but I will actually be out of town, and I'll actually be out of town for the next 2 60 Minutes in Spaces. And so we will probably have a substitute astronomer or space scientist who will be coming to give the June and July presentations. But when I return, I'll be happy to answer a question from the audience. So with that, I am happy to take questions from the audience. Yes? Okay, so the question is, how long does it take for 2 black holes to merge? And I think, so I'm not an expert on black hole mergers because I've never done research on it, but what happens is that it starts out very slowly, but what happens is over time, as more and more radiation, gravitational radiation removes energy from the system, they spiral in faster and faster. So these mergers that we see in galaxies, when galaxies collide and merge, that process can take hundreds of millions of years. So you might have heard that our Milky Way galaxy is currently on a collision course with the Andromeda galaxy. So we will have a merger with the Andromeda galaxy about 1 billion years from now. So that's nothing that we'd have to worry about. And it's and that merger, where the two galaxies eventually merge to form one galaxy, that will be a process that takes hundreds and hundreds of millions of years. And so I'm guessing that based on the fact that these processes can take so long, that will probably still be enough time for the two central black holes to merge. So once those two galaxies kind of merge together, where you can't really tell them apart, you would have to probably go into a computer simulation to find out exactly how long for those black holes to merge, but I'm guessing it'll probably be on the order of millions of years. But what will happen is that they might be on these long distant orbits for millions of years, and then as you get closer and closer together, it might be let's say 100,000 years for them to close like 90% of the way, or 50% of the way, but then it only takes 10,000 years to close the other 90% of the way. So it gets faster and faster as they get closer and closer together. Yes, sir.
Yeah, so given some of the latter results that you showed about the population 3 stars about 400 million years after the Big Bang, and some of the early galaxies that formed between 780 million years after the Big Bang, that first plot you showed was a flux as a function of wavelength of the quasars.
Mm-hmm.
Given those latter results, I don't think we can assume that metallicity is 0 when for those AGN.
Mm-hmm.
Do you know what assumptions they made for the metallicity in the models they used to produce?
I'd have to. So the question is, if we look back at this figure, these population 3 stars, these first generation stars, are probably not first generation, which is actually it's quite perceptive, and it's probably correct. Let's see. Wait, was it this figure, or was it one of the?
It was the first figure that you showed for the first paper.
Oh, it's this one, right?
It was back further. The one that had 3 data points.
Okay. Let's see. There we go. This one. Okay. Yeah. Yeah, because those supermassive first-generation stars probably lived for only a few million years. So if you expect the first stars to show up within a few million years after the Big Bang, I mean, people don't quite know. It could be a few million years, 10 million years, 100 million years. That's what telescopes like JWST and future telescopes, what they'll be looking at. But it's also with current technology, it's also very difficult to determine whether you have 0 heavy elements or you have the amount of heavy elements. The term is metallicity. The amount of metallicity, or amount of metals, amount of heavy elements, is so low that your telescope can't really tell that it's any different from 0 just because of the noise. So I think for these results, if you're looking at the first 400 million years, the first several hundred million years, given the fact that how noisy some of these results are, I'm guessing that there's kind of a broad range where you can say that these could be population 3 stars or first generation stars, if only because we can't reduce the noise low enough for us to really tell that it's 0 heavy elements or a little tiny, just above 0 in the heavy elements. So it's really coming down to just how good our instrumentation is currently.
Gotcha. Thank you.
Yeah. Yes.
I have 2 questions.
Mm-hmm.
One is, was that time-lapse photography for the globular cluster when you see all the movement all around it, or was it that animation?
Oh, that video of the globular cluster was just a computer simulation. So those orbits, probably, globular clusters are actually these extended objects that are many light years across. So we're seeing orbits that would probably take, tens of thousands of years, hundreds of thousands of years, sped up to something that we can see. So yeah, that's definitely an animation. Mhm.
Okay, when you're describing hundreds of thousands of years of time frame for black holes emergence, what about the time frame to go from the Big Bang and all the stars to the actual structure of a planet? You go from helium and hydrogen to heavy atoms and
Yeah, so the question is, we've seen kind of the early evolution of the universe, the first stars, first galaxies. So how long does it take to get from those first generation stars to the first solar systems, to the first planets? Well, we know that in our solar system, we have lots of elements heavier than hydrogen and helium. And even if you were to form a solar system with just hydrogen and helium, you had, let's say, a first generation star that's just purely hydrogen and helium, those stars would blow up pretty quickly within a few million years. So even if you had, gas giants form, actually it wouldn't be possible for gas giants to form, because part of the reason that those first gen stars are so massive is that it actually has to do with the fact that you have heavy elements, because those heavy elements allow you to actually radiate heat and energy from these clouds of gas, and allows smaller clumps of gas to collapse into stars and to form planets. But if you had only hydrogen and helium and you didn't have those heavy elements, those gas clouds couldn't radiate away the energy, and so they would actually remain gas clouds. And so the reason why you have these supermassive stars is that if you just have, you're basically waiting for an instability for the whole gas cloud to basically collapse on itself. And so that's why you end up forming a star that's 1,000 times or 50,000 times the mass of our sun. And so you really do need heavy elements to actually create planets. And so the big question is, how quickly do those stars form? How much heavy elements that they generate, and how much do they disperse into the interstellar, intergalactic medium, and how long it takes for that material to be recycled into future generations of stars. So right now, I'm not sure people have, they might have guesses that we might have, stars and solar systems and planets in the first billion years, but whether, they might occur within 500 million years, 500 million years, or 300 million years, 200 million years, I'm not sure people can really say. So they're just guesses. But I'm guessing that people might say within a few billion years, there's probably been enough generations of element recycling and heavy element recycling that you're starting to see solar systems like we have today. But between 100 million years and a billion years, nobody really knows. Yes?
Are you able to comment on the recent increase in solar activity and its interaction with Earth and our magnetic field and what all's going on there?
Yeah. So the question is about the recent increase in solar activity, and you've probably heard in the news about being able to see aurora down in Colorado, or even further south. And aurora are caused by solar wind particles, particles from the sun slamming into the Earth's magnetic field, and they get funneled into our polar regions. And they, when those particles hit molecules in our atmosphere, they can ionize those molecules or cause them to light up. And so that's why you see this red and green glow in the atmosphere. And it's actually not really anything to be too worried about, in the sense that this is actually part of a natural cycle with the sun. So the sun goes through this 11-year cycle where it increases in activity and it decreases in activity over those 11 years. And when it's at solar max, when it has maximum activity, you see lots of sunspots, and those sunspots are associated with regions where you can have flares, meaning bursts of electromagnetic radiation from the sun, but you can also have these coronal outbursts where you actually have ejections of gas and material of particles from the sun. And So the sun is always active, and it's always pumping out solar wind, those particles. It's always having flares, but that activity just increases and decreases on this 11-year cycle. And what can be, what can feel like it's rare is having lots of flares and having lots of outbursts happening all, back to back. And again, it's actually not rare. It can be somewhat rare for them to be pointed in exactly the right direction for them to hit us. Or actually, when the outburst comes out, it has to be pointed ahead of us, because by the time that it takes to get out to Earth's orbit, a couple of days have lapsed, and so the Earth has to run into it in its orbit. If it was pointed directly at the Earth when the outburst occurred, it will have missed us by the time those particles arrive at where we are, 93 million miles away. So there isn't, from what I've seen, there isn't any greater or less activity on the sun than has historically been true. It's just that, with the internet, people are just more aware of when these things are happening, and you're told, oh wow, I have to go out and look at this. And so lots of people do, and they take lots of pictures, and they post them on social media, and then other people are spurred to go out and do the same. But that's a great question. Yes, sir.
When you are taking measurements like for something like that in space for objects that are really, really far away, how do you know that there's not something in between the two that's affecting what you're seeing? Do you subtract that out, or how do you?
Yeah, so that's an excellent question. How do you know that when you're making these measurements, there isn't something in the way that's affecting what you're seeing? And it is something that astronomers have to worry about. And in this case, we're seeing, the actual observations are these 3 points, those red measurement points, and the error bars are the vertical lines, so they give you an error in the amount of light, but the horizontal lines tell you how broad of a region within the wavelength regime that those filters are set to. So basically, something that's narrow means that they're only letting in just a narrow part of the light centered around those wavelengths, whereas a broad band like this tells you they're letting in a lot of light across lots of wavelengths. And but there are other observations. We saw spectroscopy like this one here. So these are lines where they're looking at a single spot. So basically that one center pixel, that brightest pixel where the crosshair is the light from that single pixel. And basically this region here is again, the region, the pixels around that other spot. And here you do worry about gas that's in front of, in between us and this distant galaxy. And what saves you is the fact that the universe is expanding. And so what is happening is that because the universe is expanding, depending on how far away a blob of gas is from you, it's moving at different expansion rate. And so something that's further away is moving away faster. And so if there was a blob of gas or a bunch of blobs of gas between us and this galaxy, we would see lines associated with that gas, but at slightly different wavelengths because they're moving at different velocities. But there are other clues as well, because unless those blobs of gas are also being heated by some source that's emitting lots of ultraviolet radiation, it's unlikely you would see those same emission lines. So here we're seeing hydrogen beta, or H beta, these oxygen 3 lines. That's what these O3 stand for. And those are emission lines, meaning they're caused by ionization. The UV radiation is lighting up the gas. And so for contamination of, you would have to have the exact same type of contamination exactly on top of that same pixel to be affecting these results. What's more likely is that you have gas that's intervening in between us that's not being heated up by some light source, by other stars, or by another galaxy. And instead, that gas would absorb light and you would actually see it via different types of absorption lines. So it turns out that there's a whole subfield of astronomy where people were actually looking for absorption lines, so basically looking for gas clouds between us and more distant galaxies. And they're using those lines and the fact that the universe is expanding to basically give them a sense of what the gas clouds are between us and these distant galaxies. Yes?
Hi, I have a question about the virial theorem.
Mhm.
So it was regarding one of the things in it was like the velocity of the galaxies. Was that the individual galaxies, like their velocity, like how quickly they're moving around like a center, or was that the entire mass moving?
Yeah, so for the Furor theorem, when we're talking about the velocities, they're actually the measured velocities of each galaxy. And when you take velocity measurements in astronomy, unfortunately, you can't measure the sideways motion. You can only measure the in and out, or the radial motion. And that's only because when something's moving towards you, the light is blue shifted, and when it's moving away from you, it's red shifted. So you only get a sense of the velocity in this radial direction, moving either towards you or away from you. But we know that when something is orbit, the motion isn't purely in and out, it's also some sideways motion as well. And so the reason why you want to take an average is that if you have an ensemble of galaxies or stars that are all in orbit around each other, if you measure the motion of one galaxy or one star, that's not really going to tell you anything, because that's only going to tell you the motion of that one star. But if you take all of the motions, some galaxies might be orbiting like this, and so there's going to be very little radial motion, but other galaxies will be orbiting like this, and when it's in its orbit where it's moving towards you, it's going to have maximum blue shift, and so maximum motion towards you. So if you average out the motions of everything, that should give you a good sense of the kinetic energy and the velocities of everything, even though you're only measuring the radial or the in directions towards or away from you, and you're missing the sideways motion.
Follow up to that, sorry.
Mhm.
So when you're measuring that, it's only possible to measure the velocity when you have other items that you can use to see relative to it. Like you could just one singular galaxy and you can't measure it this way. You can only really see this direction. So is that how they're able to do that then?
Yeah, so the way that it would actually work is that, and part of the problem is that you don't necessarily have a fixed reference point. So the Earth is in orbit around the sun is in orbit around the galaxy, and our galaxy is expanding in the universe along with other galaxies. And so you can actually tease out all these different velocities that are causing you to move in different directions. And what you can do is you can take out the effects of all these other motions, and in the end, you can refer the motions to just the rest frame of that cluster. So if you can imagine some imaginary point in the center of that cluster that everything is in orbit around, it's probably not a single object, but if you averaged up all the velocities, so that on average there would be zero relative to that point. And so that's what you're kind of measuring in reference to, really, if that makes sense. Okay. Yeah. All right, so maybe one last question?
I think when you were showing the Dorado group slide, up in the upper left-hand corner of the slide, was that a lenticular?
There it is.
Keep going.
So here's the Dorado group.
Oh, I think it was, okay, is that lenticular up there in the left-hand corner?
The upper left?
Yes.
That's probably a spiral, just because it's so flat. So spiral galaxies are basically, they're disks with gas and dust, and I can't really make out any gas, but let's see. So we think, if this is sort of one way to understand how you can tell. I guess there's also a chance that this could be an extremely elliptical galaxy that's cigar shaped. And so the only way to tell would be if you were to take a spectroscopic measurement and to measure the velocities, the same way that we were talking about earlier. And if the velocities show that one side of that cigar was moving away from you, and the other side was moving towards you, and that means there's rotation in that disk, and then that tells you it's a disk galaxy. Because in a disk galaxy, basically all the stars and the gas clouds are orbiting more or less in the same direction. So that on one half of the disk, it's moving away, and on the other half, it's moving toward you. But if you were to take spectra and you found that the velocities were all kind of jumbled, then that would tell you it's an elliptical galaxy. But if I had to guess, that would just because it's so flat, I would guess it's a spiral, just because for a really cigar-shaped elliptical, like really cigar-shaped ellipticals like that are extremely rare, and so you would have to see it exactly, perpendicular to you to see it that stretched out. So, probably 90% of the time, or 95% of the time, if you saw something like that, you would guess it's a spiral. But the only way to be sure would be to actually measure the velocities. But wonderful question. All right, well, thank you very much. And I'll be back for the August 60 Minutes in Space. So take care, everyone.